Thank you, Phil. Ladies and gentlemen, topic of my presentation is flooding of inline flocculated tailings after tin lift drying. This is the outline of my presentation. Practically, I'm going to talk about the dual polymer injection system that we choose for inline flocculation. And we are going to talk about static flooding, flooding with wave action, and wave simulation, and I will share some of the results of this work. Canadian Natural is committed to developing energy resources in a sustainable and responsible manner to minimize the environmental impact of the operations. Over the last decade has invested in several innovative tailings treatment technologies. The key technology for tailing management at Canadian Natural is non-segregating tailing, or NST. And 2015 is going to be a big year for us, and we are excited to start our thickeners in 2015 and following that our NST operation. Canadian Natural has looked into different tailings treatment technologies to add flexibility to its potential tailings treatment approach. During 2012 till 2013, Canadian Natural identified and evaluated approximately 100 tailings treatment technology using COSIA information and roadmap study as a guideline. As a result, dual polymer injection with multi-layer tin lift drying was selected using Canadian Natural's internal technology evaluation criteria. In this picture, this is the picture of Horizon External Tailing Facility. In east side of the tailing pond is our extraction and mining operation. The west side of tailing pond, or the upland area, is a birch mountain with a natural slope of 1 to 3%. This natural topography gives us opportunity to utilize this area as a deposition area. This upland area will be submerged underwater as tailing pond is rising, and the idea was to utilize this area before it's submerged under the water. Practically, the plan was we take MFT from tailing pond, treat it, deposit on the slope, the runoff water will back to the tailing pond, and after 1 year, after the deposit passed through a 1 freeze-thaw season, it will be submerged under the water. This will give us opportunity not only with eliminating of rehandling of the material, but also with minimizing our footprint for tailings operation inside the perimeter of our tailing pond. But this idea triggered many questions, many operational questions. People, they were asking, okay, is the technology ready to deploy? How we are going to mix this polymer? What is the best optimum thickness for drying? What is going to happen for this material after submerged under the water? Is it going to stay stable, or it is going to be resuspended and back to the MFT form? What is going to deposit behave when we have a wave action in a tailing pond in a windy condition? Do we have any concern with slope stability or not? After all these questions, practically that trigger all these key considerations for this technology development, we developed a testing program. And because this testing program includes several expertise and skill set area, we hired different groups to work together as a team. Practically, turbo engineering is executing this test program, and Patterson and Cook is helping turbo engineering with doing more of the rheological analysis, inline flocculation system design, and we have SNF Energy working with us with providing their expertise on polymer and chemical treatment for the material. The test program is developed in 4 stages. The first stage is the feasibility study, practically to evaluate the performance and stability of treated material under the water. The second stage is rheological analysis of treated material to identify the required mixing energy and estimated beach runout. Practically, this stage is going to give a data for cell design and for operational design perspective. The third stage is design and operation of inline flocculation loop. With design and building a dynamic inline flocculation system, we will be able to identify and define the operational envelope and condition. The last stage 4 is the evaporative drying analysis to optimize tin lift deposition strategy, getting what's the optimum thickness and what's going to be the deposition strategy. Today I'm going to share with you the result from first stage feasibility study. This program is ongoing, and in future opportunities we'll have a chance to share more of the information with you, but today we will focus on the feasibility study. The objectives of feasibility study was investigate the effect of process water flooding on strength and solid content of dual polymer treated MFD derived selected solid content. Investigate the effect of wave action on strength, solid content, and resuspension of dual polymer treated MFD. Provide preliminary data for subsequent evaporative drying and rewetting test program. This test program is designed to test the impact of flooding in static condition and dynamic condition, or flooding with wave action. We chose to use a dual polymer flocculation mechanism because we believe that with adding another stage of polymerization, adding a cationic on top of the anionic flocculant, we are able to utilize more mechanism of the flocculation. In addition of the bridging, in addition of the neutralization of the charge of the surface, and we can utilize the electrostatic patch model mechanism as well in order to enhance the flocculation and to get a bigger size floc and a stronger floc. For anionic polymer, we used FlowPam NRG 1330, is a high molecular weight, medium charge density polymer. For cationic, we used FlowPam NRG 2880, low molecular weight, high charge density. These chemicals are provided by SNF. And the polymer concentration we use is 0.4%. Quality of treated material identified by visual inspection, and this was one of the challenge, and this was the area that SNF was really helpful to work with us to practically do visual inspection that the material is on spec or off spec. In this video, practically, please pay attention to the structure of treated material. Here is a MFT with anionic flocculant, and we are going to mix, and you can see the flocculation process. The video is recorded by SNF. This is the MFD treated with anionic polymer. Now we are adding cationic flocculant. Practically, addition of cationic flocculant is helping with generating a much more bigger size of the floc and releasing a higher quality of water. The material we used Canadian natural MFT with solid content 28.5% and fine content 99.8%, and processed water that we used contained 0.34% solid. For static flooding purposes, practically we use 90-watt halogen bulb and fan for drying of the material. to 60, 70, 80, and 90% solid content. And we use both single layer and double layer deposition for this study, and all tests were conducted in triplicate in order to ensure reproducibility of the data. In order to simulate the drainage condition, we used a 10-liter perforated pail placed inside the 20-liter pail to collect drained water. Dry deposits submerged under processed water and monitored for 14 days for strength degradation and solid content. In this video, practically, this is the wave simulation. We used the flume and we put 35 centimeters of water on top of the deposit, and that's the way that practically we generate the wave. For this flume, the target solid content was 80 and 90%. We used 2 layers of 10 centimeters of deposited material, and we put 35 centimeters of water. For flume number 1, the target was 90% solid content, overmixed material with medium shear stress level. Flume number 2, 80% solid content, optimum mixing with medium shear stress on the deposit. And flume number 3, 80% solid content and optimum mixing with high bed shear stress level. Dry deposit flooded and monitored for 12 days for strength degradation and solid content profile. In order to mimic and simulate that what is happening in reality at site, we took the 2011 meteorological data from Horizon site, and we did analysis on the wind speed that's happening at site. The data shows that the maximum wind speed we have at site is 14 meters per second, but the accuracy is very low, and the average is 2.7 meters per second. The direction of the wind mainly is across the tailing pond from northeast to southwest side of the tailing pond. It means that the generation of the wave is happening in that direction. As a result, practically we choose wind speed of 3 meters per second and 8 meters per second for our test analysis. We calculated that 3 meters per second wind speed is equivalent to 4 centimeter high wave, and 6 meters per second wind speed is equal to 8 centimeter high wave. The fetch length that we used for this calculation was 500 meter, water depth 35 centimeter, and practically we expose the deposit 2 times per day for the interval of 30 minutes for each time. For the calculation of the wave height, we used the SMB equation for shallow water waves. We got the height and period of the wind, and we used the 80 wave theory for calculation of orbital speed and shear stress in the bottom of the pond or on top of the bed. Here is some of the results from static flooding test, double layer with bottom drainage. Practically, after placing material underwater for 14 days, in the first 7 days, we saw a rapid reduction in solid content of the material. Practically, the decrease it happened from 60, 70, 80, 90% solid content to number between 50 to 60 in 7 days. But after that 7 days till end of 14 days, we don't see any change in solid content. In order to ensure that nothing happened in longer time, we keep this sample in the lab to make sure that with the 3 or 6 months later, still we have the same solid content as well. We measured the average wind shear strength as well. We see the similar phenomena that first 7 days we see a rapid reduction in strength, which dropped from 60 to 200 kPa, below down close to 10 kPa, and practically all sample, except sample dry to 90% solid content, exhibited peak wind shear strength higher than 5 kPa after 14 days. The sample that practically was dry to 90% solid content, it showed more degradation when it comes to the strength and solid content. Another parameter that we were monitoring was the solid content in the processed water itself, because this is going to give indication that if we do have some resuscitation of the particle back to the process water, during that 14-day practically the solid content in process water remained under 1%, and practically it indicates that there is no resuspension of the clay particle back to the process water. Here is some result with the wave action. Similar to the static test, solid content dropped from original to between 50 to 60% solid for all samples. And for the peak vein shear strain, range between 2 to 8 kPa after 7 days for all samples, and between 4 to 9 kPa after 14 days. All samples except the one with 90% initial solid content exhibited strength higher than 5 kPa after 12 days. The reason that we were looking for 5 kPa because that was one of the criteria for the technology approval, that even after submersion under the water, it will deliver the requirement by the regulators. Again, we looked at the solid content in process water, and still after 12 days, the solid content in process water remained below 1%, which again, it indicates there is no resuscitation of the clay particle back to the process water. As a conclusion, testing exhibited submerged deposit of dual polymer treated MFT is a feasible concept. However, Canadian Natural is not pursuing this technology as it is currently not economically justifiable, because we do have some options with our improving our NSD to deliver our regulatory requirement, and practically this is going to be plan B in a case that if we face any challenge. Deposit dry to 80% solid content remained above the AER D74 requirement. Wave action similar to that expected in the field did not result in considerable resuspension of the deposit. Material with initial solid content of 80% or higher resulted in less than 5 kPa strength after flooding. Material with initial solid content less than 80% resulted in strength higher than 5 kPa. And as a result, optimal target solid content before re-wetting should be between 70 to 80% solid content. I would like to acknowledge the work that Turbo Engineering, SNF Energy, and Patterson & Cook they did on this project, and they are committed, they are working hard, and I'm hoping in close future we will be able to share more information regarding this exciting project. Thank you.